Welcome back and happy Monday. Actually, very good day. Looks not that cold, not that bad, sunny. Um, okay, so what we gonna do? Let's check if I'm recording this. I think yes, you're fine. So we talked about instruction set architecture last few weeks, and we want to move to instruction set now. Instruction set architecture and also performance, and anything regarding to performance like benchmarking and those kind of stuff are important to sometimes you as an engineer. You need to uh, decide which hardware is better, or you need to kind of find performance for different computer to choose which one is better. Okay, so today we're going to talk about instruction set, and we're going to talk about different type of instruction set, reduced instruction set architecture, and reduced instruction set architecture and complex instruction set architecture. We'll talk about that and start a new language, assembly language for this machine called RISC-V. We're going to talk about that, start it. And you have assignment that you have 1 week regarding instruction sets, but you can't start it today. I know you're going to leave it end of the week, but I just posted that because every week we have assignment, like 2-3 questions, very simple to just don't forget. Yes.
How do the assignments fit into the grading for the syllabus? Because it didn't look like there's like a quiz part of the grade portion, but there wasn't really one outline for the assignments.
Yeah, 20% is assignment. So we don't put that much mark, like 1.5 or 1.2. It's not that much, but it's little by little. Yes, it's part of your assignment. 20% of your course is considered assignment. Okay, so this is what we're going to talk today. RISC computers and CISC computers, comparing them, and go for RISC-V instruction set. So regarding to ISA, what we covered, we said, okay, ISA is just interface between hardware and software, and defines what kind of instruction CPU support, and in programming points of view, of course. And when you compile a program, this instruction gonna get created, these instructions coming from compiler, and different processors kind of sometimes having same ISA instruction set architecture. Why? Because they want to be compatible. Like Intel's and AMD sometimes wants to compete to each other. They want to have same actually programs without changing, be portable in different machines. So they use same ISA instruction set architecture. So that's something that we covered. We had this diagram showing ISA, but about ISA, some parts is always similar. All of, we can say most of ISAs have some operations for arithmetic operations like add, subtract, sometimes multiplication, sometimes actually add immediate. Add immediate means you are adding a constant with register and put in another register. Or like different type of arithmetic instruction, like shift, I think also consider arithmetic. We also have some instructions regarding to load and store. Load and store are type of instructions than working with memory. Working with memory, because memory is kind of I/O as well, input output, is very slow. Working with memory compared to CPU is so slow. So sometimes we need to have different instructions for them. And those kind of computers actually that we want to talk about, they have different instructions for load and store. We're going to see why. And control instructions. Some instructions, like a branch, you need to change the control of the code, jumping up, jumping down, when you are jumping up, most of the time you are doing a loop. When you are jumping down, most of the time you're changing just control, if and else, for example. Yeah, so these three types of instructions are common in most of instruction set architectures, including what we're going to talk today that's called RISC-V. So ISA defines what the processor does, not how it's implemented. So for this chapter, we're not going to the hardware. We're not going to the CPU, how it works. We're just in like a higher level, we're looking how a programmer can use CPU using the language that machine support, that we call it ISA, instruction set architecture. But ISA or instruction sets were not always same. They also evolved from the time that the first computer came up, because the computer was so simple, instruction set was also very simple. And then it started getting more advanced. And in that time, instruction sets also start getting advanced. It becomes like a bigger instructions to do with one instruction, do many things, with one instructions. But after years, we hit to power wall. Remember, we talk about when we start making the hardware more complex, because if the instruction is complex, if the instruction is big, the hardware that's supposed to execute that instruction need to be also complex. And complexity always bring up more power. You need more power for that CPU if it's more complex. And power always hitting to power wall. If it's more than 100 watts, is not good for CPU, and it's hard to cool it down. So in that case, they started make the instructions again simpler. We started from simple instructions, become complex instruction, become again simple instruction that new computers mostly use the type of instruction set that called reduced instruction set, RISC, that the computer that we're going to work on is also RISC. So we're going to talk about these two types, RISC and CISC. So instruction sets always balancing between simplicity and performance. How, if the instruction is complex, it needs more complex hardware, that the performance going down. This is something that we need to consider, is always between the balance between simplicity and performance. And early computers were very simple because the technology wasn't that big to have better instructions. But modern computer still start getting simple because we hit what power wall. Because we hit power wall, we start make the CPU simpler, and how we make the performance higher with actually parallelism. With parallelism, that one of them is actually like superscalar or multi-core or pipelining that we're going to see in this class, you can do parallel thing at the same time. That's called parallelism. And it's coming from simple structure. You make simple structures, but multiple of them. If the computer is simple, everything is regular. The instructions are regular. When you want to fetch them, they are all similar. You don't need some of them 2 cycle, some of them 1 cycle, some of them 3 cycle, like what we have in Intel or in AMD. Because in AMD, instructions have different size. For some instruction, you need 1 cycle to fetch it. For some, 2 cycles and more. So the pipeline get messed. But if the computer is regular, everything is simple, everything is the same size, every step for running instruction like fetch, decode, execution, and write back taking similar time. And this similarity, this regularity makes the computer simpler to can run parallelism better without problem. Okay, so we're going to talk about those things. We have 2 structure set, complex instruction set that focus in bigger instructions and more complex instructions. Maybe you ask why we had CISC before then. Anybody can guess why we started with CISC? The CISC computers were started from 1960 in that time. Most of mainframes, like I remember that time that I had, even we had a course called assembly programming. I passed that course. And we learned how program a computer. However, we were working with mainframes computer. It was VAX computer. It was a very specific computer. And the assembly language was like C++, so advanced. Assembly language, when I'm talking about assembly language, the assembly that each instruction implemented in a hardware side. You know, for instruction, you have a hardware to do that. And that was so complex. And my question that why we had CISC, why, what you think about, why we had CISC before, why we didn't start making RISC at the beginning? Yes?
Maybe it was easier to make those complex instructions than to make the chip faster, like to make the processor faster.
Make the processor faster. So when make the instruction bigger, the processor get slower, of course. Does not get faster. Any other idea? Yes?
Well, the focus probably wasn't be general purpose, right? It was probably like just because you're making a specific technology since it was newer, so they had to have the complex instructions that like matched their system specifically, I guess.
Yeah, who gonna get benefit of having big instruction?
Well, their specialized hardware, right? Just because then it will.
No, not hardware. Yes, programmers. You make it easier for programmers to write assembly code easier, because in that time we were writing, I explained, we had a course like assembly. Why you don't have that? Because you are not writing assembly anymore. But in that time we were writing assembly code. So they wanted to make it easier for programmers instead of having like 1 instruction. That time, right now, you need to write 10 instructions to do the same thing with that, you know, because instruction was like a macro instruction, big instructions. I can show you some of those in Intel, for example, that in Intel, for example, you can add registers with memory and write it in memory. Wow, that's so complex. If you want to do that with RISC-V, you need to have like 10 instructions. Because writing with memory, you are not allowed to write memory right away. You need to work with registers because of performance and so forth. So yeah, that was because of programmers. We wanted to help programmers to write easier with the assembly language. But right now we don't need that because we have compilers, very advanced, high performance compilers that can make for us assembly very high, optimal. You don't need to write it in assembly. You write it in C++, and compiler gonna fix it for you. Compiler gonna change it to assembly, very high performance. In that time, we haven't had good compilers. So sometimes compilers generate assembly code that wasn't efficient. So programmers should go there and fix it and make it more efficient, more, a bit right, fix it. But compiler right now are very efficient and very optimal. That was the point of having CISC. But because of, what happened in complexity and power wall, we said, oh, we can go more. We can make it more complex. But some structures stayed the same. Like Intel still exists in your computers. Most of your computers are still, for example, i7 or the family of i86. We call them 86 family or x86 family. This family stayed the same. They change it, they add more stuff, but the structure is still the same. That's a CISC computer. But they try to fix this problem with multi-cores and adding extra stuff, but it still is complex. But new computers after that time that started developing from scratch, they all are RISC computer. Okay, reduced instruction set. So reduced instruction set is smaller. What is smaller? I can say everything is smaller. Size of instructions, constant, is not changing. The number of registers, constant, not changing, all same. Unlimited. When it's smaller, it's faster. The size of instruction is small. The number of registers is small. The type of instructions is also small. We don't have many type of instructions. Most of RISC computers, they have just limited number of instructions. Instructions that working with registers, we call them register instructions. Some of them working with constant numbers, we call them immediate instructions. Some of them are like a branch, jump and branch instructions for jumping and changing the control. Some of them are memory. We just have two instructions working with memory, load and stores. None of others working with memory. If you want to add, for example, two memory variables are memory. If you want to work with those, you need to load them in the register and work in registers, bit registers. Okay. Why we have different instructions for load and store? Any idea? I mentioned that at the beginning a little bit, because load and store are slow, because working with memory is slow compared to CPU. But do you think that makes the CPU slow in general? No, because the performance is overall. Do you remember when we wanted to compute performance, we were counting the number of instructions and then clock per instructions, and we find execution time for a task and reverse it. So if one or two instructions are slow, in overall not changing the performance, isn't it? If most of instructions are, for example, register instructions that are so fast, if two of them are slow, it's not changing, the average is still good. So that's why we have different instructions. Some of them are slow, but they are very limited. Most of them are fast. Working with registers are working with registers is so fast because registers are very close to CPU. They are inside CPU. And registers are very small. Here, for example, in this computer that we're going to learn, we just have 32 registers, just 32. Easier, you can address them, you can access them, and they are very close to other parts, and you can access them fast, very fast. Okay, so that's evolution of instruction sets. And so CISC computers focusing on complex instruction, and RISC focusing on performance and scalable. So this is the structure of i7. This is the CISC computer. It's very complex. And even they are module, each of those are so complex. But instructions are very powerful in CISC computer. Each one instruction can do many things. And you can have actually one very rich hardware as well. So characteristic of CISC computers, complex instruction set like Intel or family of i86 is these things. Large instructions, diverse instruction set. Like for example, Intel has 7 types of add, just one add, that in many computers is just 1 or 2 type. Add 2 registers, put in another register, or add 1 register with a number, immediate, we call it immediate number, and put it in register. It's mostly these 2 type. But in Intel, we have, I think, more than 7. We have, for example, register to register, we have immediate, we have memory to register, we have register to memory, because in Intel is 2 operand. In most of computers that we have, they have 3 operand. Like when you say add, operand is this. We say, for example, add. We have our destination and our source. They are just, these notations are not real, is not name of register. I'm just saying this is source and destination. In Intel, when you add these 2 registers, they add them together and put them again in this destination. Add them together, put them in that. They have 2 operands. So in these 2 cases, this can be memory as well. You can directly add with memory. If you just put, for example, something like that, this is the address of memory. You can address of the memory in RD. And you can add also here. It means register, add it with memory, put it again in the memory. This instruction probably in RISC is like 10 lines, but you can do it in 1 line, you know. And it's not just that. In RISC, for example, you can have different size. For example, you have many different type of registers. Some of them are 64, some of them are 32, some of them are 16 in family of Intel family. But in RISC computers, the main characteristic is regularity. Everything is regular. The size of instructions, all 32. The size of registers in the one that we are supposed to learn is 64. All registers, we have just limited number of registers, 32, and all 64 bits. But in Intel, some of them are 8, some of them are 16, some of them are 32, and 64. For example, in Intel, I wrote somewhere the number of them. I don't know if I find them. Yeah, for example, in I86, the family of Intel, um, we have 8, I don't know how many 8, but we have 8, 16, we have 832, and 1664 registers. So we have different type and different numbers as well. And we have so many specific registers as well. We have segment registers, we have floating point registers, we have vector registers, and more. We have so much because it's so complex. The structure is so complex. However, this is still very modular. If yeah, which this picture is very modular. They put them very smaller, but RISC computer is everything very straightforward and simple to understand. We can see them soon. Okay, so that's the reason that we had CISC, because of helping programmers to can write codes in assembly language easier. So this originated in 1960, and in computer like a mainframe computer was like a supercomputer that time. So the benefits and the pros was compact code. One code can do multiple things. And for programmer, it was easier, less code, and easier for programming in assembly language. But problem was complex hardware. For each instruction, you need to design a hardware to do that. And especially if the instruction has multiple different operands, it's so complex. With one instruction have multiple operands. It's very complex to implement it in hardware. So complex hardware, and the pipelining was so complex. Why pipelining was so complex? Because in pipelining, we want everything be similar. Pipelining means, for example, if one instruction need fetch, decode, execute, and write back. Imagine most of computers need these steps. Some of them more, but in most of them, fetch, we fetch it. Fetch means we bring it from memory inside CPU. That's called fetch. Decode, we decode it because it's a binary number. It's like a number. We need to decode it to see what instruction is that. Okay, is it add or subtract or whatever? And what is the operands? We need to decode it to understand. When we decode it, we understand, okay, this is an instruction, add, and it's working with these two registers and put the result in a second register, for example. That's a decode. And then execute it. We have ILU inside the CPU based off the instruction and registers and everything, execute it. For example, it's add, and we know working these two registers, adding these two registers and put it in the other one. Execute, and then we need to write back the result. And each of these need one cycle, at least. They need different cycle. When we fetch it, we can decode it. It need to step by step. So one instruction at least need these 4 steps. We can make it faster than that. We can do decode and fetch at the same time. It's not possible. But when we decode it, fetch is free. We can fetch another instruction. That's called pipelining. Pipelining means when you do decode, you can fetch the second instruction. This is instruction I plus 1, I plus 2, and decode, execute, and write back. Fetch, decode, execute, and write back, for example. So in this case, first instruction need 4 cycle, but after that, each instruction just need 1 cycle. That's called pipelining. But why pipelining not working for complex instruction sets? Because instructions are not regular. Instructions are different. Some of them are, for example, 1 word, some of them 2 words. If it's 1 word, you can fetch it in 1 cycle. But if it's 2 word, you need 2 cycle to fetch it. So you can do it like that. You're going to make lots of, we call it a stall. We need to put some stall here to make it delay, to make delay to can fetch it or decode it or execute it properly. So that's a problem with pipelining in complex instruction set computer. But still they are doing. i7 is amazing, but it makes it so complex. That's why the structure is so complex. Okay, so the key idea for CISC computer is actually instructions are the main part. The CISC favors instruction power over hardware simplicity. They want to have better instructions. They don't care about hardware complexity. They want to have a better instructions. Okay, that's called CISC. But as I said, the new computers are not CISC anymore. If we have CISC because of supporting the other computers that we had before, like Intel's and AMD, for example. But what we want to learn in this class is RISC, reduced instruction set. Reduced instruction set is smaller. Regularity is the main part. Regular, fixed length, simple instruction, load and store architecture. Load and store architecture means we have different instruction for load and store. None of instructions directly work with memory, just load and store. So we have load, most of the time LD is load, and LS load mostly work like that. For example, you are doing memory and register, RD, register destination. And so is, actually this is address, sorry. Address, for example. So what is doing, check the memory address and write it in RD. However, it has some indexing that I didn't put it here. And for store, we are register source and address. What we are doing from register source, we put in memory. Like that. It works like that. We just have these 2 instructions, load and store. However, in RISC-V, we have load 32 bits and load 64 bits. We have 2 types of load for 32 and 64 bits differently. But we just have these 2 types, load and store. This type of computer is called load store architecture. So they just have different instructions for load and store. Okay, so they rely on compiler because even the first computer RISC that developed that we're going to see that is called MIPS. MIPS didn't check at all if it's hazard happening or not in pipeline. When two instructions are related to each other, you can't put them in pipeline. They make problem. So in first computer, RISC computer called MIPS, this computer didn't check hazard at all. It just start running. It's rely on compiler. Compiler should fix it. Compiler should fix it. So if two instructions are related, like for example, you are adding a A and B putting in C, and imagine you have another add that using C and D putting in E, for example. C is the result. Imagine these two gonna get add, and the result good. The result can be used here. So it means we didn't finish the first instruction in the pipeline, and we want to use it in execution in a second instruction. So these two instructions cannot go to the pipeline directly. This is called hazard. They are dependent on each other. So this is not possible. So rely on compiler. In MIPS, we didn't fix it in a hardware level. We said, OK, compiler need to fix it. And compiler was advanced enough to find it and understand, oh, I can, because compiler make assembly code. Compiler use high-level language and transfer it to assembly code. And assembler change assembly 1 to 1 to machine code. That is a binary. OK, so rely on compiler. And immersion 9080. OK, so the pro, what was good about it? Fast, very fast. Why fast? Because regularity makes it fast. If it's a small, it's a physics, and something is a smaller, faster, because you can pass it faster, you know. And predictable. It's predictable. And pipeline, very efficient. And hardware is very simpler for design and implement, of course. But the problem was larger code. Instead of having 2 lines, you need to have 20 lines for implementing simple code. And fewer complex instructions. It's mostly software part, but because we don't program assembly anymore, we don't care about that. That's a problem of compiler. And compiler is working very good. And RISC favors hardware simplicity and pipelining, efficiency of pipeline compared to, you know, complexity of instructions. Any question about RISC and CISC? Okay. So the principle is in these 3 parts. Fixed size instruction, a small number of instructions, and in a consistent way. A smaller is always faster, limited instruction set, limited number of registers, limited addressing modes. Addressing modes means we are not working with different type of, you know, addressing mode. We just have one addressing modes, you know, and make the common case fast. Make the common case fast means most of instructions are register instructions. We can focus on those, make them fast. If 2 instructions are slow, we don't care about them. Because in average, the performance is still high. if the common instructions are fast, like what the example that I mentioned, if you have most of instructions, like 80 instructions are registers and very fast, and just 2 of them or multiple of them are slow, in average is not changing the performance. So that's makes the common case fast. It always works. Okay, MIPS was the first computer that developed microprocessor without interlocked pipeline. Without interlocked pipeline stage means it's not checking hazard at all. It's just give it to compiler to fix it. This was first a RISC computer that implemented, actually designed for simple hardware, very efficient pipeline, very simple fixed length of instruction format, just load and store to access memory, 5 stage for pipeline, instruction fetch, decode, execute, memory write back, and minimal hardware hazard handling. Just give it to compiler. That's why it's called without interlocked pipeline, because most of the hazard is not doing implemented in a hardware level. It's all given to the software to get fixed. Why MIPS is matter? Because it was the first RISC philosophy that implemented, and all of the things regarding to simplicity, regularity implemented in RISC. It was just like a basic example of RISC computer. Most of computers are compatible with MIPS, especially the computer that we're going to talk about, RISC-V, is also built based off MIPS. And we're going to talk about that. Okay, let's just start a little bit about RISC-V. RISC-V actually developed in Berkeley, is open source, kind of. When it's open, it means doesn't have license, and everything about that is available. And you can just use the same structure and change it and make a new processor. It's something for, in terms of learning, is very good processor, and is based off RISC. Everything is similar to MIPS in terms of the characteristic and the simple instruction format. What we can say about that is a modular. It has 32 32-bit and 64-bit systems. Actually, there is 2 cores for that. It's called RV32i and RV64i, one 32 and one 64-bit. And in top of that, you can actually add new instructions. You can, for example, it normally doesn't have instructions for vectors or floating point, but you can add that. That's why it's extensible structure. You can extend it. This is something that we can use for that, and is open source. I mean, it doesn't have license. You can probably find this very low, code to just implement it in hardware description language, HDL, like Verilog, for example. We're gonna work in that too later. So what else about RISC-V? It's simple, open, and flexible. So let's talk a little bit more about RISC-V before finishing that. RISC-V has 32 general purpose registers. It has 32. It's called X0 to X31. Each one 64 bits, 0 to 32. So the name of registers are X, X0, X2, X1, X2, and X31. So this is name of registers. We just have 32. We have some special registers. We call them special purpose registers. Like, for example, X0 is always 0. Sometimes we call them 0 register. It's a hard word to be 0. So for example, the reason of having one register always 0 is for some instructions. Sometimes, for example, instruction like move register destination register source, that you want to move RS to RD. We don't have this instruction like move in RISC-V. We can implement it with add and X0. So we can add, for example, X0, X1, or X2, and X1, for example, X3. So this is X3 plus 0 going to X2. It's like move. This part of my, I don't know, anything I write this side is not visible. Okay, this is like moving, using just that X0. So X0 is always 0. This is something that we need to know. So X1 is return address. We also have program counter. Let's clean up this. We have return address. When you call a function or something, the return address going there. We have stack pointer when we are working with the stack. Later we can see that. The pointer of a stack gonna go there. And the other registers are general purpose registers. Memory is very important. Memory is little endian. Little endian means like a regular. In little endian, if you want to put something inside, the least significant bit going to the lower address and the most significant bit going to highest address. You can see in that picture. So that's called little endian. And is byte addressed. Byte address means each byte in the memory is addressable, accessible. Each byte in the memory is accessible. You don't need to read, for example, one word. Word is 4 byte, and double word is 8 byte in this computer. Okay, what else? Or 32 bit and 64 bits. Okay. So load and store. Let's talk a little bit about load and store. Okay, and finish it. So yeah, that's a word and double word that I mentioned. We have these 5 different type of instructions: registers, immediate, load, store, and jump. That's all instructions that we have. So next class we can talk about like instructions, like register instructions. But I just gonna show this. It's very simple. Like add, for example, it's add these 2 and put the result in that. Subtract, do the same 2. Immediate instruction working with constant numbers. That's it. Next class, we're going to talk about the more and serial codes and some simulation to see how we can run them. Okay, any questions? Okay, see you next class.